Hello everyone. In this video I am going to explain the time response analysis of discrete time signal and discrete time system. This is discrete time system. Discrete time system. Okay, it is basically the LTI systems. So we will be talking about the time domain response of an LTI system. How we can solve a difference equation which governs an LTI system. Okay, the time response here, the time response that we will be studying is basically for the time domain behavior of the linear time invariant system, that is of course the discrete time systems, for different standard input signals. Okay, so basically there are two basic methods for analyzing the response of a linear time invariant systems for a given input signals. Okay, so the first method is the input signal. In the first method, what we do is the input signal is dissolved into some elementary signals. So of course the elementary signals is most often the unit impulse. Okay, then using the linear property of the system, because the system is already linear, that is we are talking about the LTI systems, so then using that linearity property of the systems, this response of the system to the elementary signal is added to obtain the total response of the signal, total response of the system. That means what we do is, suppose we have an LTI system, then we are applying an input, and for that input we need to calculate or find out the response, that is the output. So to get that response, what we do is we resolve the input signals into sum of elementary signals, for example the impulse, then using the linearity property, because linearity means superposition, so superimposing the sum of the signal that has been resolved into some of the elementary signals to get the total response of the system. Okay, so this already actually we have studied while we have derived the convolution. Okay, so this is nothing but the convolution, because convolution gives the same concept. I mean, based on the same concept only we have derived the convolution. So if you know the impulse response of the system, because impulse response is nothing but the response of the system due to an input impulse. So if you know that the impulse response of the system, then you can get you can calculate the response of the system by convolving the input, any arbitrary input, with the impulse response of the systems. Now in the second method, what we do is, in the second method, that we try to solve directly. That means the direct solution of the difference equation which is representing a particular LTI systems. Okay, so in that basically here I am going to explain that the second method only, because the first method already we have discussed while we have evaluated the convolution sum of a discrete time system. So here we are going to discuss the second method, in which we follow, or in the second method we try to solve the difference equation directly. So let's start. The second method, the general form of the difference equation, the general form of any difference equation which actually governs a particular equation, a particular LTI systems, of difference equation of say nth order, capital Nth order LTI system. Okay, capital Nth order say LTI system can be represented as say y of n, which is the output, of the system is equal to minus, you'll come to know why this minus, k is equal to 1 to n. Here we are talking about the nth order system, so this ak y of n minus k, then plus summation over k 0 to say another m bk x of n minus k. This is in general, okay, the general notation of an LTI system, I mean difference equation of an LTI system. So you see, when k is equal to 0, it is a0 into y of 0 y of n. So that is here, okay, and that is why this y is started from k is equal to 1, but x, so b0 x of n plus b1 x of n minus 1, so and so forth. Similarly, so this will go that side actually, that is why it is minus. So this side is the output, that is the response, and the right hand side is the input. So that is why this minus comes. Okay, and where it is ak and the bk, this will be a sequence ak and a bk. This ak, sequence ak, and this sequence bk are nothing but the constant. So these are also called the coefficient of the system. These are constant coefficient, okay, constant coefficient of the systems. Now the response of any LTI system, discrete time LTI system, can be decomposed as like this, okay. So the total response which will be equal to zero state response plus zero input response. I'll tell you what is this too. Zero input response, okay, zero state response and zero input response. Now this zero state response means this is a response of the system, is the response of the system due to input alone. That means the system is this is your LTI system, any LTI system, okay. For these LTI systems, there is suppose some input x of n and the response y of n, this LTI system, so a response y of n, okay. So the zero state response means the response of the systems due to the input alone, this input alone, when the initial state of the system, this initially there is nothing, so initial state of the system, initial state of the system is 0, okay, initial state of the system is 0. That is what is called zero state response. That means the response due to the input alone, there is nothing initially in these systems, so for which whatever be the output due to the input alone is called zero state response, okay. That means the system is initially relaxed, okay, at time n is equal to 0, okay. So the system is initially relaxed, so it is called a relaxed system, okay. The system is initially relaxed, that is why there is no initial state of the system, so the response is due to the input alone, and which is called the zero state response of the system. On the other hand, the zero input response, this zero input response is the response of the response of the system due to the initial state of the system only. That means this is the output zero input response, that is the output y of n of the system when the input is 0, okay, when the input is 0. That means you are not applying any input, but you are getting some output, okay. Of course that output, that is the response, is because of the some initial state within the LTI system itself, okay. So that is what is called zero input response. So these two, hope it is clear, zero state response. So zero state response means you are applying an input and only for that input you are getting the output. That means the system is initially relaxed. It has initial state 0. So that is 0 state response. And 0 input response means you are applying input 0, but you are getting some response of the system which is due to the initial state of the system, that is 0 input response. And the total response of the system is the combination of 0 state response and 0 input response. For example, suppose let us consider a first order discrete time system. So let us consider a first order discrete time LTI system, or simply the system. Okay, discrete time LTI system. So for the first order discrete time LTI system, the difference equation will be your y of n is equal to some a of y of n minus 1, okay, a of a into y of n minus 1, since it is first order means n is 1, and plus x of n. Okay, so this is in general the first order discrete time systems. Okay, first order discrete time system which is being defined using a difference equation like this. So let the input sequence xn. So this is your, of course, input is xn. So input is xn. You are applying to a system, and the response of the system is y of n, and this y of n is being defined like this. Okay. So let your input. Okay. Let your input let your input be let the input sequence be 0. Let the input sequence x of n is 0 for all n less than 0. Okay, for all n less than 0. Okay, the input sequence is 0 for all n less than 0. Okay, and the initial condition of yn and initial condition of yn for say n is equal to minus 1 exist. Okay, minus 1 is exist. That means your y of minus 1 is not equal to 0. There are some values. Okay, and the successive value of yn for n greater than equal to 0. So successive value of yn, your successive value of yn for n greater than equal to 0 are as follows. Okay, so for n is equal to 0, what you will get? Y of 0. So as per the given difference equation, what will be y of 0? Y of 0 is your a y of minus 1 plus x of 0. Similarly, your y of 1, similarly for your y of 1 for n is equal to 1, so y of 1 will be your, what will be y of 1? A y of 0 plus x of 1. And from the previous one, y of 0, you just put the value of y of 0. So what was y of 0? It is a y of minus 1 plus x of 0 then plus x of 1. So it will be your a square y of minus 1 plus a into x of 0 plus x of 1. So similarly, your y of 2 will be a y of 1, a y of 1. So your y of 2 will be a into y of 1 plus x of 2, which is nothing but, again just put the value from here, y of 1. So a square y of minus 1 plus a x of 0 plus x of 1. So it will come out to be your, a cube y of minus 1 plus a square x of 0 plus a into x of 1 plus x of 2, and so forth. So and so forth. Then for all n, it will be y of n is equal to a n plus 1 y of minus 1 plus a n x of 0 plus a n minus 1 x of 1, then plus the so and so forth, and finally x of n. Now this can be written like a to the power n plus 1 y of minus 1 plus summation over k 0 to n, okay, 0 to n a to the power k x of n minus k, okay, x of n minus k for all n greater than 0. Okay, now this particular stuff y of minus 1, it depends on the initial condition. So it is the initial value of the system. It depends on the initial value of the system, okay, or initial condition of the system, okay. And this part is depends on the present input, depends on the present input, okay, depends on the present input. Now suppose this y of minus 1, so when it is 0, when y of minus 1 is 0, then the output y of n, then your output y of n, it depends only on the input, it depends only on the inputs, okay, it depends only on the input applied. So whatever be the input applied, so hence y of n is known as the zero state response. So therefore if y of minus 1 is equal to 0, then whatever be the yn, so if y of minus 1 is 0, y of n will be only this part, and that part is the zero state response of the system, okay. So this zero state, therefore the zero state response, also called the forced response, okay, forced response, okay. So also called the forced response of the system is, let me write it like y of f for forced, okay, and is equal to summation over k your 0 through n a to the power k x of n minus k, okay. Now if the system is initially non-relaxed, that means y of minus 1 is not equal to 0. If the system is initially non-relaxed, that means y of minus 1 is not equal to 0. So then that means what I mean to say, suppose y of minus 1 is not equal to 0. What does it mean? It means the system is initially non-relaxed, and the input, suppose input x of n is 0 for all n, okay, for all n, suppose x of n is 0, that means you have not applied any input to the system, okay. So then the output of the system, then this output y of n, output of the system y of n depends only on the zero state, zero state response, that means y of minus 1 only. Okay, zero state of the system, not the zero state response, zero state of the system, that is y of minus 1 only. Okay, that means, what I mean to say, that if y of minus 1 is not equal to 0, that means the system is initially non-relaxed and the applied input is 0 for all n, then the output of the system yn depends only on the initial state of the system. Okay, then the response of the system is called zero input response. Okay, already as I mentioned, and also called the natural response. So okay, so at that condition the response of the system is called the zero input response, also called natural response. Why natural response? Because you have not applied any input, so whatever be the response you are getting naturally, so that is why it is called natural response. So let me denote it as y of n for natural. Yn of n will be, then what it will be, n plus 1 y of minus 1. Okay, for all n greater than equal to 0. So that means this is your force response, also called zero state response, and this is your zero input response, also called the natural response of the system. Now the nth order difference equation for the LTI system, that is this equation. Okay, these nth order difference equations for LTI systems can be written like this way also. Okay, can be written like, say, summation over k 0 to n a k y of n minus k. Okay, all the y I am writing in the left hand side, and in the right hand side summation over k 0 to, say, m b k your x of n minus k, where n is called the order of the difference equation, and that means the order of the system. If the coefficient a naught, so here there will be a naught. In the previous equation we originally we have omitted that a naught at the beginning. Now if a naught is not equal to 0, so what we can do is, if suppose a naught is not equal to 0 or not equal to, not equal to 1, if it is not equal to 1, then what we do is, if it is 0 then it will be 0 only. So if it is not equal to 1, then what we can do is, we can divide the whole of this equation, okay, whole of this equation by a naught, okay, to normalize the equation. So the solution of the difference equation can be expressed as a sum of the two parts, that is your natural response and the force response. Okay, also this natural your natural response is also called homogeneous response, remember. So natural response, that means zero input response, also called homogeneous solution, and also called complementary solution, and force response or the zero state response is also called the particular solution, okay, also called the force response. Okay, so the solution yn can be written like this: y of n, which is equal to y, say, h of n, that is homogeneous solution, plus y p of n, that is your particular solution of the difference equation. Okay, so this particular method I'll explain with an example now. So let us consider one example. Say a discrete time system is characterized by the following difference equation. Say y of n plus 5 y of n minus 1 plus 6y of n minus 2 is equal to say x of n. Determine the step response. The question is determine the step response of the system. Step response of the system. Here is the solution. For the given difference equation, the total solution, as I already mentioned, that your y of n is your homogeneous solution, and the particular solution, homogeneous solution, also called the complementary solution. Okay, complementary solution. Then what we do is first we determine the complementary solution. So how will we do the complementary solution? By setting x of n is equal to 0. That means the complementary solution is the zero input response. That is your homogeneous solution, that is zero input response. Okay, so how will you calculate that the x of n is 0? And when x of n is 0, here in the given equation, when x of n is 0, this is in the given equation, when x of n is 0, whatever be the y of n you will get, so let it be in the form of like lambda to the power n. Okay, so let it be in the form of the lambda to the power n. If it is y of n is the lambda to the power n, when x of n is 0, then from the given equation here, what you will get? You will get lambda to the power n for y of n plus 5 into lambda to the power n minus 1 plus 6 into lambda to the power n minus 2 and is equal to 0. So lambda to the power n, 5 into lambda to the power n minus 1 plus 6 lambda to the power n minus 2 is equal to 0. Okay, and obviously from this we easily can have from this we can, if we make say lambda n common, then it will be your lambda n common, so it will be lambda square, lambda n common and then make it 0, so it will be lambda square plus 5 lambda plus 6 is equal to 0. Okay, now this becomes a quadratic form. Lambda square plus 5 lambda plus 6, it's a quadratic form, quadratic equation. So there are two solutions, and I hope you understand. If you do the factorization of this, then it is lambda plus 3 into lambda plus 2. So therefore two roots of the solution, roots of this quadratic equation will be lambda 1, which is equal to minus 3, and lambda 2, which is equal to minus 2. So therefore the complementary solution, that means your zero input response, will be of the form, because it is lambda we got minus 3 and the minus 2, so in this form. Okay, so therefore your y of n, that is your complementary solution or the homogeneous solution, that is zero input response, is some constant times minus 3 to the power n plus some constant minus 2 to the power n, because there are two roots. Okay, so the solution will be like this. Then comes to the, so this is your complementary solution. Now comes to the particular solution. So for the particular solution, that means zero state response. Okay, or also called natural response. So for that particular solution, what we'll do is particular solution means, that means the forced response, or also called zero state response. That means initially the system is relaxed and the response of the system is due to the input only. Now what is your input? Input is state input as per the given question, that determine the step response. Step response means the response of the system due to the input step function, that is unit step. Okay, so therefore as you know that the unit step is or since it is denoted as step, not exactly unit step, so step is nothing but k into some k is any value, k into un. Okay, un actually unit step, that means the value is 1. So when it is step, so the value can be other than 1 as well. So let me put it as k. So the particular solution for the step input, that means there is no initial condition of the system, that the system is initially relaxed. So therefore ypn, that is particular solution, is equal to k. Okay. Now for lambda for n greater than 2, why n greater than 2? Because as you see in the given equation, if n is equal to 0, we need to have y of minus 1, because right now we are talking about the zero state response. That means the system is initially relaxed. That means all the initial values are 0. So if we start from n is equal to 0, what the initial values we need? Y of minus 1, because n is 0 means y of minus 1, since it is a second order system. So y of minus, here we need y of minus 2. That means for n is equal to 0, what we need? We need y of minus 1 as well as y of minus 2. Then for n is equal to 1, we need y of minus 1. Okay. Now since we are talking about the particular solution, that is your zero state response, so initially it is relaxed. That means y of minus 1 and y of minus 2 is 0, so we must start from greater than 2. So therefore n is greater than 2. So if for n greater than 2, this yp of n, which is equal to k, and x of n is equal to 1, let me if I am considering k here, so x of n can be 1 for unit step. Okay, 1 for unit step, and the unit step means, as you know, from 0 to infinity it is 1 1 1, and I am considering from 2, so from 2 also it is 1 1 1. Okay, towards the infinity it is 1. So x of we put yp of n is equal to k and x of n is equal to 1 for n greater than 2. I hope you understand why n greater than 2 is considered. Okay, now from this if we see, then what it will be? It will be k, because yn, that is ypn, which is k, then 5k, then 6k, and is equal to 1. Okay, so k plus 5k plus 6k is equal to 1, and from this it becomes 12k is equal to 1, so k is equal to 1 by 12, so therefore yp of n is 1 by 12. So therefore the total solution, I mean the solution of the total solution, or total solution of the system will be y of n is equal to the complementary solution or the homogeneous solution or the zero input solution plus zero state solution or the zero state response or the force response or the particular solution, which is 1 by 12. Okay, so complementary is C1 into minus 3 to the power n plus C2 into minus 2 to the power n, and particular solution is 1 by 12. Okay, now from 0 onwards you calculate. So for n is equal to 0, from this what you will get? Y of 0. We have to calculate the C1 and C2, right? Okay, for that n is equal to 0. So let me put n is equal to 0 in the given equation. So in the given equation, when n is equal to 0, what you will get? You will get your y of 0, then 5 y of minus 1 plus 6 y of minus 2 plus x of 0. Okay. Now since in the given example the initial values y of minus 1 and minus 2 are not given, so let me put it as 0. So y of minus 1 and y of minus 2 both are equal to 0, then therefore y of 0 will be equal to x of 0, which is equal to 1. So as you see here, this for n is equal to 0, y of 0 plus 5y of minus 1 plus 6y of minus 2, x of 0. Now since the initial values are not given, so let me put y of minus 1 and y of minus 2 as equal to 0, so therefore y of 0 is equal to x of 0, which is equal to 1. Okay, now for n is equal to 1, so what we will get? Y of 1 plus 5y of 0 plus 6y of minus 1 is equal to x of 1. So x of 1 is again 1 because it is unit step is 1, so then y of 1 will be minus 4, because y of minus 1 we consider to be 0, so y of 1 will be minus 4. So therefore from the previous one, that is this C1 minus 3 to the power n plus C2 minus 2 to the power n plus 1 by 12, what we get is minus 3 minus 3 because your what we get is y of 0 we got 1 and y of 1 we got minus 4. Okay, so let me put first for n is equal to 0. So if in this n is equal to 0, it is c1. Okay, that is y of 0. Y of 0 will be minus 3 to the power 0, 1. So it is c1 plus c2. Minus 2 to the power 0 is 1. So c1 plus c2 plus 12. 1 by 12. And y0 is 1. So actually what happened, since there are two constants, c1 and c2, to find out two constants c1 and the c2, we need at least two equations. Okay, so the first equation will be for y0. So when it is y of 0, it will be c1 plus c2 plus 12, 1 by 12, which is equal to y0. Y0 is equal to 1. Okay, so therefore c1 plus c2 plus 1 by 12 is equal to 1. And for the second y of 1 will be minus 3 c1, because minus 3 to the power 1 is minus 3. So minus 3 is c1. Then minus 2 to the power 1 is minus 2. So minus 2 c2 plus 1 by 12 is equal to y of 1. Y of 1 is minus 4. So then there are two equations for evaluating c1 and the c2. Now simply solve these two equations. Okay, these two equations you will get c1 is equal to 27 by 12 and c2 you will get minus 16 by 12. So therefore finally y of n will be 27 by 12 minus 3 to the power n, then minus 16 by 12, your minus 2 to the power n plus 12, 1 by 12. So this is your final solution for the given difference equation. This one for this given difference equation the response of the system given by this equation due to the step response. Okay, due to the step input. Response is the output. Okay, so now what we'll do is this I have explained with an example the procedure of your solving a difference equation or finding out the response of a discrete time system in terms of the homogeneous solution or the complementary solution or the zero input response plus the particular solution or the force response of the systems. Okay, together is the total solution, and we have evaluated these 12 examples. Now let me make it generalized. So till I have explained this process with an example, now I'll do it in general for any LTI systems how we evaluate this yn. So I'll make it in general. So in general, the nth order discrete time system equation, that is for any LTI system, can be written like this way. So k is equal to 0 to n ak y of n minus k, which is equal to k is equal to 0 to m bk x of n minus k. So where n is called the order of this difference equation or order of the system. Now if this since I have written it from k is equal to 0, so there will be a0, okay, y of n. So this a0, if this a0 is not equal to 1, then already I mentioned if it is not equal to 1, so we have to normalize by dividing the equation with by a naught to normalize. Okay. So the solution of the difference equation already, as I mentioned, can be written like in terms of this homogeneous solution. Okay, so homogeneous solution y h of n plus the particular solution y p of n. Okay, so or now homogeneous solution, which is also the natural solution or the natural response, which is the zero input response, that is x of n is 0 for all n is equal to 0. Okay, so we'll start with the natural response. So natural response for the system, so that means it is 0 input response. Okay, 0 input response. So this natural response or the 0 input response. So now since it is natural response, therefore this input is 0, that means this right hand side is 0 because it is 0 input response. So right hand part is 0. So therefore your summation over k 0 to n a k y of n minus k is equal to 0. Okay, so now the solution for this, which we'll call it as say y h of n, can be written like some constant lambda to the power n. Okay, lambda to the power n. And now if we substitute the lambda to the power n instead of y, then we can write it like this, say summation over k 0 to n a k lambda to the power n minus k is equal to 0. So where we are considering or assuming that a0 is 1 for the time being. If not, then we will normalize it by dividing the whole equation by n. Okay, so from this what we can write is, say for k is equal to 0, a0 we are considering 1, so it is lambda to the power n, then plus a1 lambda to the power n minus 1 plus a2 lambda to the power n minus 2, then a3 lambda to the power n minus 3, and so on and so forth. And we'll, since it is up order n, then it will be like say a n minus 1 lambda to the power n minus 1, so it is n minus n, capital N, plus 1, and the last term will be your a n lambda to the power n minus n is equal to 0. Okay, is equal to 0. So therefore, if we make a lambda to the power n minus n common, lambda to the power n minus n common, then what we'll get? We'll get lambda n, then plus a1 into lambda n minus 1, then a2 into lambda n to the power n minus 2, and so on and so forth. It will be a n minus 1 lambda, because n minus n is made common, then finally the a n, which is equal to 0, and from this we will get lambda to the power n plus a1 lambda to the power n minus 1 plus a n minus 1 lambda plus a n is equal to 0. Now this equation, if you look at, this is a polynomial equation. Okay, so this is a polynomial equation order n. Okay, and at order n. So this polynomial equation is called the characteristics equation of the system. Now since the order is n, so it is an nth order characteristics equation, and which can be expressed in the factorized form as like this. So it can be written like lambda minus lambda 1 into lambda minus lambda 2 dot dot lambda minus lambda n is equal to 0, where this lambda 1, lambda 2, lambda 3, this up till lambda n are the roots of the characteristics equation this. Okay, so these are the nth root of the nth order characteristics equations. So this root of the characteristic equation are called the characteristic roots or characteristics roots or eigenvalues of the systems. So these roots are called lambda 1, lambda 2, this lambda 1, lambda 2, these are called the roots of the characteristics equation, that is the characteristics roots, also called your eigenvalues. Okay, also called your eigenvalues. Eigenvalues. Okay, these are eigenvalues of the system. Now the nature of this of the natural response, depends on the type of these roots, whether these roots are real or imaginary or simply complex. Okay, so the roots lead to a real exponential or imaginary roots to real roots leads to real exponential, imaginary roots to sinusoidal, and complex roots to complex damped sinusoid. That means if the roots are real, then this leads to an exponential. If the roots are imaginary, then it leads to a sinusoid, and if the roots are complex, then it leads to exponentially damped sinusoid. Now, if the roots lambda 1, lambda 2, lambda n are distinct, then it has n solutions. And what will be the solutions? So the solutions will be like, say, C1 lambda 1 to the power n, then C2 lambda 2 to the power n, and so on and so forth, Cn lambda to the power capital N. And in that case, the general solution it can be of the form like this. It will be like this. Homogeneous solution in general will be like, say, C1 lambda 1 to the power n plus C2 lambda 2 to the power lambda 2 to the power n, and plus so and so forth, say plus Cn lambda to the power n. So here it is small n. Okay, lambda to the power n, where C1, C2 dot dot Cn are some arbitrary constants. So these constants are determined by applying some initial conditions. For example, if the roots are, say, lambda 1 is equal to 2 and lambda 2 will be 3, suppose it is a second order only, then lambda 1 and lambda 2, so lambda 1, say, for example, 2 and lambda 2 is, for example, 3, then this homogeneous solution will be C1 into 2 to the power n plus C2 into 3 to the power n. Okay, if the roots are distinct. So this is the case when these roots lambda 1, lambda 2, lambda 3, this up till lambda n, if these roots are distinct. Okay, if these roots are distinct root, then the solution will be like this way, and as a result the general solution for the homogeneous response or homogeneous solution, it will be C1 lambda 1 to the power n, C2 lambda 2 to the power n, and dot dot plus Cn lambda to the power n. Okay, and if the roots are repeated roots, if the roots are, say, repeated roots, then say, for example, say, if lambda 1 repeat m times, suppose this your root lambda 1, it repeats m times, for example, so that the root of the multiplicity of m and the remaining n minus m, capital N remaining capital N minus m roots are distinct. then these things are distinct then, and the characteristics equation of the systems can be written like lambda minus lambda 1 to the power m, then lambda minus lambda m plus 1, lambda minus lambda m plus 2, and so and so forth. It will be lambda minus lambda n is equal to 0. And then the general solution will be your yh of n will be your c1 plus c2 n, then your c3 plus c3 n square plus likewise cm n to the power m minus 1 into whole into lambda to the power lambda 1 to the power n. Okay, then plus lambda cm plus 1 into lambda m plus 1 to the power n plus cm plus 2 lambda m plus 2 to the power n, and so forth, plus cn lambda 1 to the power n. Okay, so for example, if the roots of the characteristics equation say lambda 1 is minus 2, lambda 2 is also minus 2, and lambda 3 is your say 2. Suppose there are 3 roots, 2 roots are repeating, that is suppose lambda 1, for example, this is just for example, lambda 1 is suppose minus 2, and lambda 2 is also minus 2, that means it is repeating, and then lambda 3 is suppose 2, then the solution will be like this, yh of n will be c1 plus c2. So where c1 is minus 2, c2 is also minus 2, that is why it is repeating like this way, and whole that is minus 2 to the power n, and plus c3 to lambda 3 is 2, so c3 into 2 to the power n. Okay, so this is in case of the repeating root. So in case of the repeating root, suppose the first root lambda 1 is repeats m times, then the remaining n minus m, there will be remaining n minus m roots. So therefore lambda minus lambda 1 to the power m, lambda minus lambda m plus 1 into lambda minus lambda m minus 2, and so forth. So finally the solution will be, for this it is c1 plus c2n plus c3n square, so forth up till m, so cmn to the power m minus 1 whole into lambda 1 to the power n, and for the remaining root cm plus 1 lambda m plus 1 to the power n, cm plus 2 lambda m plus 2 to the power n, so forth cn lambda 1 to the power n. So this is shown with an example. This. Now if the roots are complex, then how can we write? If the roots are complex, then we can write like, say for example, lambda 1, say let it be lambda 1 is equal to lambda say a plus ab form if it is complex root. Similarly, say lambda 2, for example, it's a suppose complex conjugate of this, then it will be a minus jb. Then the homogeneous solution will be, say yh of n will be your r sum r to the power n a1 cos of n theta, because it is in terms of the complex, so it will be a1 cos of n theta, a2 cos of sine of n theta. Okay, and where this r will be nothing but square root of a square plus b square, and the theta is the arctan of b by a, tan inverse of b by a, and a1 a2 are any constant. So this is how we do for the natural response in general. Now coming to the forced response or zero state response. So now for the forced response or zero state response. Okay, so for this, the forced response, as already we know, there is the solution of the difference equation for the given input when the initial conditions are 0. That means the output or the response is due to the given input only. So it consists of again two parts: homogeneous solution and the particular solution. So the homogeneous solution can be obtained from the roots of the characteristics equation, and the particular solution, that is to satisfy the difference equation for specific input signal for n greater than equal to 0, because there is no initial condition. In other words, the particular solution is a solution that satisfying the given difference equation in the form say 1 plus summation over say k is equal to 1 through n a k. Instead of y, we'll write it as yp for the particular solution, yp n minus k, and is equal to summation over k 0 through m 0 through m bk x of n minus k. Okay, so the general form for of this particular solution for several inputs are given, can be derived like if the input is a step input, like already we have seen in previous example, that if the input is steps, then that particular solution can be simply a constant k. If it is something like a into say m to the power n, then the solution will be k m to the power n. Similarly, say a to the power n, n to the power m, then it will be like k naught n to the power m plus k1 n to the power m minus 1 plus dot 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 say up till km. Okay. Likewise, for different input, we can have different solution. So the forced response of the system is obtained by summing the particular solutions and the homogeneous solution, and then finding the coefficient in the homogeneous solution so as to combine the response yHn, that is homogeneous part, plus yp of n, that is the particular solution, which must satisfy the 0 initial conditions. Okay, with an example I'll show you. So let us take one example. So the given difference equation is y of n plus 2 into y of n minus 1 plus y of n minus 2 plus is equal to x of n plus x of n minus 1. Now suppose the question is to find the natural response. So natural response means 0 input response of the systems, which is being described by this difference equation with the initial conditions. Suppose the initial conditions are given. Initial conditions y of minus 1 is equal to say 1. Here we need y of minus 1 and y of minus 2 as the initial condition, so y of minus 2 is also suppose 1. Okay, now the question is to find the natural response. Okay, natural response. Okay, that means 0 input response. That means you are not giving any input, depending on the initial condition only what are the outputs. Okay, so from this given difference equation, the homogeneous equation can be obtained by equating the input 0, because 0 input response. So equating the input terms to be 0. That means it will be your y of n plus twice y of n minus 1 plus y of n minus 2 is equal to 0. So the homogeneous solution will be for this y, say h of n is equal to some lambda to the power n. Lambda to the power n. So therefore from this it will be your lambda n plus twice lambda n minus 1 plus lambda n minus 2 is equal to 0. So from this I am suppose making lambda n minus 2 common, so it will be lambda square plus twice lambda plus 1, which is equal to 0. So from this your lambda square plus twice lambda plus 1 is equal to 0, and the roots will be, that is nothing but your lambda plus 1 whole square, which is equal to 0. So therefore lambda 1 is just minus 1. There will be two roots, but both the roots will be equal, so lambda 2 is also minus 1. Okay, now since the roots are repeating, then the general form of the homogeneous solution will be already, as I mentioned, that for the repeating roots. So the general solution of the homogeneous equation will be, say, yh of n, which will be as per the repeating roots, say c1 minus 1 to the power n plus c2n a minus 1 to the power n. Okay, now in this equation, if we put n is equal to 0, so then yh of 0 or simply 0 y0 will be equal to c1, and y of 1 will be minus c1 minus c2. Now our objective is to find y0 and y1. Okay. Now go back to the homogeneous equation. So given equation, homogeneous equation, that means this one. So in this equation, if we put say for n is equal to 0, then it will be y of 0 plus twice y, this will comes from this one. Okay, sorry, y of 0, then twice y of minus 1 plus y of minus 2 is equal to 0. Now it is given that y of minus 1 is also 1 and y of minus 2 is also 1. So therefore y of 0 plus 2 plus 1 is equal to 0. So therefore y of 0 is minus 3. Similarly, if we put n is equal to 1, then what we will get? Y of 1 plus twice y of 0 plus y of minus 1 is equal to 0. Okay, so here y of 1 will be, y of 0 is 1, so 2, then y of minus 1, sorry, y of 0 is already we obtained minus 3, so it is minus 6, and y of 1 minus 1 is 1, so your minus 6, 1, so minus 5, so it is y of 1 is 5. Okay, so therefore putting it in this equation, so therefore what you will get? You will get your c1 is equal to y of 0, so that is minus 3, and minus c1 minus c2, which is your y of 1, that is equal to 5. Now solving these two equation, we will get c1 already minus 3, and if we put c1 minus 3, so it will be c2 will be your minus 2. So this is your c1 and this is your c2. Now put these values of C1 and C2 in this solution. Okay. So finally your natural response is y of n, yn of n, that is n for the natural response. So minus 3 C1 to the power n, so minus 1, lambda 1 to the power n, C1 into lambda 1 to the power n, so C1 is minus 3, so lambda 1 is minus 1 to the power n, plus C2 into n into lambda 2 to the power n, so C2 is minus 2, okay, and lambda 2 is also minus 1, so minus 2 and 2 minus 1 to the power n for n greater than equal to 0. Since it is n greater than equal to 0, we can put un. Okay, so that is the natural response. Now for the same example, suppose you need to calculate the forced response as well. Forced response. So forced response due to the input only. Okay, so the forced response due to the input only. Suppose the input is x of n. Suppose the x of n is equal to half to the power n u of n. Suppose this is your input given. So for this input only you need to calculate the force response. So the force response due to the x of n is equal to half to the power n u of n. Okay, so already that homogeneous solution we obtain like this. So here it will be the force response will be the homogeneous solution plus the particular solution. So already we have obtained the homogeneous solution like y h of n as your C1 into minus 1 to the power n plus C2 minus 1 to the power n, because lambda 1 lambda 2 both are minus 1 repeated root. Okay, now the input is your x of n is equal to half to the power n u of n. Okay, so the particular solution will be, say, yp of n will be some k times the constant half to the power n u of n. That will be the particular solution. Now if we put this yp of n and the x of n, okay, into the difference equation, the given difference equations. So the given difference equation is this one, yn plus twice y of n minus 1 plus y of n minus 2 is equal to xn plus x of n minus 1. So it will be like your k times half to the power n plus twice k half to the power n minus 1 plus k half to the power n minus 2 is equal to half to the power n plus half to the power n minus 1. Okay, now for n is equal to 2, why n is equal to 2? Already in my previous example I have mentioned, because here also as you see this y of n minus 2 terms is there. So now we are calculating the force response, and force response is the zero state response. That means the output due to the input only, there is no initial condition. That means initially the system is relaxed. So since the initially system is relaxed, there is no value for y of minus 1 and y of minus 2. So we should start from n is equal to 2, where it will be for n is equal to 2, it will be k half square plus twice k 2 minus 1 1, so half plus k half to the power n minus 2, that is 2 minus 2 0, is equal to 1 by 2 whole square, that is 1 by 4 1 by 2 to the power 1, so it is 1 by 2. Okay, that means it is here 1 by 4k plus k, so it will be twice k is equal to, it will be your 3 by 4. Okay, 3 by 4. So from this k will be equal to 1 by 3. So therefore the particular solution, your y p of n, k is 1 by 3, so 1 by 3 into half to the power n into y of n. So the total force response, will be your the homogeneous solution plus the particular solution. So it is your C1 minus 1 to the power n, C2n minus 1 to the power n. So this mass is the natural solution, that is the homogeneous solution, plus 1 by 3 into, because it is particular solution is 1 by 3 half to the power n. U of n means it is for all n greater than 0. So now from this, again you need to calculate the C1 and the C2. So for that we have to put first y of n is equal to 0. So y of 0 will be your C1 plus 1 by 3. And for n is equal to 1, y of 1 will be your minus C1. Okay, minus C1 plus minus C2 plus 1 by 6. Okay, again you need to calculate this y0 and y1, y0 and y1 to find out the C1 and the C2. So in a given difference equation, if we put n is equal to 0, so it will be y0 plus twice y of minus 1 plus y of minus 2 is equal to x0 plus x of minus 1. So here y of minus 1 and y of minus 2 are 0, because we are calculating force response, and for force response there is no initial condition. Initially the system is relaxed. So therefore y of minus 1 and y of minus 2 both are 0. Then since the input is half to the power n, so for n is equal to 0 it is 1. For n is equal to minus 1 it is 0. So therefore y of 0 is equal to 1. Similarly, if we put n is equal to 1, so it will be y of 1 plus twice y of 0 plus y of minus 1 is equal to x of 1 plus x of 0. Now in this case y of 1, your y of 1 will be equal to, this is y of 0 is 1, already we have calculated, so it is 2. Okay, it is 2, then it is 0, then it is x1 is your half to the power 1, so that is half, x of 0 is 1, so it will be, this is your half, half plus 1, and this is your 2, so that side it is minus 2, so it will be minus half. Okay, so we got the your y0 and y of 1. So therefore if we go back to this y0, which is c1 plus 1 by 3, y1 minus c1 minus c2 1 by 6, in which we will now put y0 and the y1, where y0 is your 1 and y1 is your minus half. So your c1 plus 1 by 3 is equal to 1 from this previous equation, then c1 will be 2 by 3, and the second one was minus c1 minus c2 plus 1 by 6 is equal to y1, so y1 is minus half, so therefore c1 plus c2 1 by 6 that side, so it will be 2 by 3, then c2 will be 0. Okay, then combining both, finally the force response will be your 2 by 3, that is your C1, minus 1 to the power n plus 1 by 3. This is your n, this is your the total force response, C1 minus 1 to the power n, then C2 n minus 1 to the power n, 1 by 3 half to the power n. So where we obtain the C1 to be 2 by 3, C2 is 0, so 2 by 3 minus 1 to the power n, then 1 by 3 half to the power n. Okay, so we'll get force response 2 by 3 minus 1 to the power n, then 1 by 3 into half to the power n. Of course you can put together a un. Okay, so this is the final force response. Now I'll show you that the same response, that is time domain response or time domain analysis of the discrete time systems, can be evaluated, or time response can be evaluated using Z transform. Okay, rather it is easy. While I explained the Z transform, I mentioned that Z transform makes the calculation easier. Let's see how. Okay, with an example I'll show you. Suppose the example is to find the impulse response. That means to find the output of the systems due to the input impulse of the systems described by this difference equation. Say y of n minus 3 y of n minus 1 minus 4 y of n minus 2 is equal to x of n plus twice of x of n minus 1 using Z transform. Okay, so let's see how. So the given difference equation is y of n minus 3 y of n minus 1 minus 4 y of n minus 2 is equal to x of n plus twice of x of n minus 1. Now if we apply the Z transform along with its properties, you will see that y of n, Z transform y of z, minus 3, since it is linear, Z transform is linear, so minus 3, y of n minus 1 means z inverse y of z, applying the shifting property. So minus 4, so since it is y of n minus 2, so it will be z to the power minus 2 y of z. And similarly it is x of z plus twice z inverse x of z. Now from this, if we get the y of z, so what will be the y of z? Y of z is y of z into 1 minus 3 z inverse minus 4 z inverse 2, and this side x of z, if we make common, then it will be 1 plus twice z inverse. So if now we divide, if we make it in the rational form, say yz divided by x of z, that is y is output, x is input, so it is known as transfer function. So it will be 1 plus 2z inverse divided by 1 plus 3z inverse minus 4z inverse 2. Next is just to find out the inverse Z transform of this h of z. You will get h of n, because h of n is the impulse response. Okay, so just simplification. This will be your, if we make z comma, if we do this 1 by z, then it will be z plus 2 whole into z. Similarly here will be 1 by z. So this z actually comes from the denominator where it is 1 by z square. Okay, 1 by z square, here it is 1 by z, so z cancel, z will be there. So here in the denominator it will be z square minus 3z plus 4, then do the factorization. So in the denominator, okay, this z will go that side, h of z divided by z for the partial fraction method. So z plus 2, it will be z square minus 3z plus 4. Okay, the factors will be z minus 4 and z plus 1. So h of z divided by z will be, say, z by a by z minus 4 plus b by z plus 1. Now if we solve it out, okay, if we solve it out for a and b, you will get a is equal to 6 by 5 and b is equal to minus 1 by 5. So therefore finally h of z divided by z will be 6 by 5 into 1 by z minus 4 minus 1 by 5 1 by z plus 1. Okay, now this z is there, 1 by h of z by z, z is there, so you make z that side. So here will be z, here will be z. Okay. Now simply you make z common here. Okay, so it will be 1 minus 4z inverse, it is 1 plus 1 plus z inverse. So it is nothing but 1 by 1 minus 4z inverse, that is inverse will be, as we all know, it is 4 to the power n u of n. It is something like a to the power n u of n. Z transform is 1 by a minus z inverse, where in case of a here it is 4. Similarly, since it is plus, so it will be minus 1 to the power n u of n. So this is the solution. You see how easily we can calculate this using Z transform. Let us take another example. Determine the unit step response. That means similar one already we did by solving the difference equation. So determine the unit step response. That means the output due to the input unit step of the system whose difference equation is, say, y of n minus 0.7 y of n minus 1 plus 0.12 y of n minus 2 is equal to x of n minus 1 plus x of n minus 2. Now the initial conditions are given, y of minus 1 also, plus y is equal to y of minus 2 is equal to 1. Okay, we will do it in using Z transform. So simply taking the Z transform both sides of the given difference equation, so it is y of z minus 0.7 y of n minus 1, for that it is z inverse y of z. But practically there will be, since initial conditions are given, but that means the system is not initially relaxed. So therefore, along with this, in general we do it like z inverse y of z, but practically it is z inverse y of z plus y of minus 1. Okay, similarly 0.12 y of n minus 2, so for that z inverse 2 y of z, but practically it is z inverse y of minus 1 plus y of minus 2. Similarly, in the right hand side it will be z square x of z plus x of minus 1, z to the power minus 2 x of z plus z inverse x of minus 1 plus x of minus 2. Okay, now just put the substitute the initial conditions. So y of minus 1 and y of minus 2 as given as 1. Now what will be x of minus 1 and x of minus 2? X is the input, and input is given here as unit step, and as we know, unit step is equal to 1 for all n greater than equal to 0. So for n less than 0 it is 0. So therefore x of minus 1 and x of minus 2 is 0, since it is step. Okay, just put the initial values, then it will be y of z minus 0.1 z inverse y of z plus 1, then 0.1 to z inverse 2 y of z plus z inverse plus 1 is equal to z inverse x of z plus z inverse x of z. Okay, z inverse to x of z. Okay, now what will be the x of z? X of z is the z transform of x of n. What is x of n? X of n is the un. So x of z will be 1 by 1 minus z inverse. So just put the value here in the x of z as 1 by 1 minus z inverse. Okay, so therefore y of z will be 1, y of z is equal to 1 minus 0.7 z inverse plus 0.12 z inverse 2. Now if we calculate, it will be minus 0.58 plus 0.12 z inverse is equal to z, that is for 0.12 into 1, the 0.12 and minus 0.7. So for that this minus 0.58 comes, and 0.12 z inverse, then z inverse by 1 minus z inverse, z inverse 2 by 1 minus z inverse because of x of z and x z inverse x of z. Okay, z inverse x of z and z inverse 2 x of z. Now simplifying this expression, we obtain this. Okay, y of z, z inverse plus z inverse 2, and if we do the factorization it will be like this. Okay, and for this part again z is made common, so z in the numerator it will be z into z plus 1, in this denominator it is z minus 1, then z if we do the factorization of this part 0.4, 0.3, and 0.4 plus 0.3 is 0.7. So likewise z minus 0.4, z minus 0.3. Similarly, this part will be in the numerator is this, denominator the factorization of this part. So z minus 0.4, z minus 0.3. Why we do this factorization? To get the inverse Z transform. Again, using the partial fraction method, this z and from here one more z common, so that z will be that side, so it will be z plus 1 divided by these things, and this will be your here it is not z square, it is z, okay, it is z, so 0.58 z man 0.12 because this z made common, okay. And do the partial fraction using partial fraction methods, simple algebraic partial fraction method. Finally, you will get this 4.762 by z minus 1, 23.33 z by z minus 0.4, like this you will get, okay. And then you just simply take the inverse Z transform. So it is 1 by z minus 1, 4.762 into 1 by z minus 1, that is your this z will come that side, no? This z, if we multiply, then this z, so this z will come here. So z by 4.762, y of z will be 4.762 into z by z minus 1. So z by z minus 1 is nothing but un. That is actually 1 by 1 minus z inverse. Okay. Similarly, this will be 0.4 to the power n un. Okay. This one, this constant 23.33. This is 23.33. Okay, this is 23.33. Then z by z minus 0.4, that is 0.4 to the power n u of n. Similarly, for this it will be 0.3 and u of n, and like that. Okay. So here it will be 23.33, 0.4 to the power n u of n, and here one more will be there, no, 1.12 into 0.4 to the power n u of n. So combining both these two, it will be 0.22.21, 22.21, 22.21, 0.4 to the power n, and this your 18.57 into 0.3 to the power n u of n minus 0.54, sorry, 18.57.3 to the power n u n, and here it is minus 0.54 or 0.3 to the power n u n. Together will be 18.03, 0.3 to the power n u of n. Okay, so this is your final solution. So the same solution, if we would like to do using the process of solving the difference equation, then we have to go for the method that I explained, the force response method. Okay, to find out that, because it's a force response. Force response means the zero state response. Okay, output due to the input only, and finally the total solution is the natural response plus the force response. Okay, so the process is lengthy, but while you use the Z transform, the process becomes simpler. Okay, so for that you need to do the Z transform, I mean take the Z transform of the whole equation. Okay, then if it is force response, then put the transform of the input instead of the x sub z and do the simplification, and finally do the inverse Z transform to get y of n. Okay, so this is how we do the analysis of the discrete time LTI systems in time domain. Okay, so time domain response, zero state response, zero input response, from which we got the force response and the natural response. So similarly for the force response, we got the homogeneous solution and the particular solution, and finally combining both we will get the total solution of the systems. The same solution can be done using the Z transform. For that you need to take the Z transform of the equation, then put the given condition and all, and finally take the inverse Z transform. Okay, so this is all about the time response analysis of this. So in my next class, next video, I'll explain the frequency response of the LTI systems. Hope you understood up till this. If you have any query, kindly contact me. Thank you for listening.